In this section we're going to talk about the continuity of a graph. In calculus and a lot of other mathematics, we like to work with continuous functions because they have a lot of characteristics that allow us to do things like differentiate, integrate, etc. And sometimes we can get around that, but it's just easier to work with functions that are continuous. So some examples of continuous functions would be something like a polynomial function. So this would be something like x squared, x cubed, something like that, where we have values of our variable to powers. So it could be something like x to the fourth plus 3x cubed plus 2x plus 1. Those are types of polynomial functions. So it could be a polynomial function, and some trig functions are continuous. For instance, the sine of x and the cosine of x are both continuous functions as well. Now there's some functions that are only continuous over particular intervals. So the two functions, or the three functions that we just mentioned here, are continuous on the interval from negative to positive infinity. So that would be one way we could say it. We could also say negative infinity less than x less than infinity. A couple things to keep in mind: you never have equal signs for infinity, so we never bracket infinity either. So these are examples of continuous functions. Now some functions are not continuous over their entire domain, but they're continuous over parts of the domain. So for instance, y equals square root of x. We've looked at this graph before. It looks something like this. We can tell that it's not continuous for all values of x, but we can tell that it is continuous on the interval from 0 to positive infinity. And again, we bracket 0 because it's continuous at 0, and we don't bracket infinity because we can actually never reach infinity. Now let's go ahead and look at some functions that are discontinuous. So for instance, an example of a function that's discontinuous is the tangent function. Just as a quick example, another example is the secant function. Well, let's go ahead and look at the tangent function. And actually, before we get started too far, let's go ahead and talk about exactly what continuity means. I think we all have an intuitive idea what it means, but let's go ahead and look at it kind of from the layman's point of view, and then we'll have a formal definition for it. So continuity basically means I could take a graph and I could trace it and never have to lift up my pen. Okay, that's a pretty nice little definition. So now let's look at the tangent graph. Just as a quick side note, you should know how to graph the sine curve, the cosine curve, tangent curve automatically and instantly. Things like the secant curve, cosecant, cotangent, you should be able to come up with them given, enough time. But the other three graphs I mentioned, sine, cosine, and tangent, you should be able to graph without even hardly thinking about it, because they're going to be handy functions to be able to work with. Okay, so the tangent graph. So if we look at the tangent graph, we have to understand that the tangent function is made up of a ratio of the sine function over the cosine function. So where the cosine is equal to 0, I have a little bit of a problem. So again, tangent is equal to sine over cosine. Okay, where does cosine equal 0? Well, cosine equals 0 at pi over 2. Cosine equals 0 at 3 pi over 2, 5 pi over 2. Again, we're going to see a trend here. So because it equals 0 there, I have a vertical asymptote. Now this is going to hold true at negative pi over 2, at negative 3 pi over 2 as well. I'll have vertical asymptotes here because the cosine of negative pi over 2, it's actually the coterminal angle to 3 pi over 2, the cosine is 0 for those functions as well. So I have these vertical asymptotes. Now the tangent graph, the tangent of 0 we know is 0. The tangent of pi is 0, so I know they're going through these points right here. And I see a lot of patterns here, but we'll talk about exactly what these vertical asymptote patterns mean in a second. Now I have a couple of options. The tangent graph could start toward positive infinity and go toward negative, or it could start at negative infinity and go toward positive. And if you plot some points, you could figure this out pretty fast. But one quick thing I would note is 0 to pi over 2 is the first quadrant, and in the first quadrant tangent's positive, so that means my graph has to be up in this area. So this is what my tangent graph looks like. And that repeats over and over and over again. And if you notice, that has a period of pi. It's kind of an interesting characteristic of this graph. So if I tried to trace this graph from here to here and then have to jump back down again, I definitely have to lift up my pencil. So I see that this has a discontinuity. So this is a real quick note. You should be able to graph the tangent graph along with the sine and the cosine graph as well. Now let's talk about these vertical asymptotes. These are discontinuities. And not only are they discontinuities, these are places where the function f of x equal tangent of x is undefined. Okay, so how would we describe those? Well, it looks like this pattern continues and it starts off at negative infinity, dot, dot, dot. Then I see I have a discontinuity at negative 3 pi over 2, negative pi over 2, positive pi over 2, positive 3 pi over 2, positive 5 pi over 2, and then this pattern continues. Well, one thing I notice here is that pi over 2 seems to be common. Now the coefficient in front of the pi over 2 seems to be an odd value. 3, 1, 1, 3, 5, and some of the values are positive and some are negative. So a way I could write this, instead of saying what x can be, let's say what x cannot be. X cannot be, okay, first of all, 2n plus 1. If I plug any integer in here, positive or negative in for n, and multiply it by 2 and add 1, it's going to produce a negative value. So if I take 2n plus 1 times pi over 2, and in this case we can say something like where n is any integer, and of course integers include positive and negative values, I could talk about what my domain is and where I have discontinuities. So if I talk about the domain, this is x cannot equal. If I talk about discontinuities, I would say I have discontinuities at x equals. So you kind of have to frame that equal or not equal to depending on whether you're talking about the domain values or values where the discontinuities could exist. When we're talking about discontinuities, sometimes we like to talk about the definition or working with point continuities. So let's go ahead and look at the definition of point continuity, and then we'll kind of pull that into the idea of a continuous graph. So we're talking about point continuity at the point x equals c, where c is some constant. Now this definition of point continuity definitely will be on a quiz, definitely will be on an exam, so you need to know this. And when I say know, I mean memorize this. Well, there's three rules that we want to keep in mind here. First of all, the function evaluated at that x value of c must exist. That means there cannot be a hollow point, there can't be a vertical asymptote, and the graph actually has to exist. So for instance, if I talked about the square root of x, if I talked about point continuity at x equal negative 10, that graph doesn't even exist at negative 10 because I can't take the square root of negative numbers. So the first rule of point continuity is the function must exist at that point. The second rule of point continuity says the limit as x approaches that same value from the right and from the left, of course, must exist. So the point must exist, the function must exist. Now another way to say must exist is to be defined. Now the third step here is the limit as x approaches c of my function has to equal f of c. These have to be equal, and what this means is the limiting value and the functional value must be equal. Okay, so that's our definition of point continuity. Well, next what we want to look at is we want to look at some graphs that kind of show whether a point at x equals c is continuous or discontinuous. So let's go ahead and look at an example. So for this example, let's go ahead and sketch up a quick graph. And we'll put a hole in the graph here, and then we'll have a solid point right above it. And I'll draw my favorite parabola. Parabola opening up. So this is the question. Is this graph continuous at the point x equal 2? So that's my question. Well, intuitively, before we even answer this mathematically, if I were to draw this graph, clearly I'd have to lift up my pen to jump to here to trace this. So intuitively, I say that no, this graph is not continuous at 2. Mathematically, let's go ahead and check that for point continuity. So we are going to check point continuity at x equal 2. Now remember, there's 3 things I need to check for. First of all, the function must be defined at 2. So if I plug 2 in, I get 3 back out. So check. Yep, function's defined. Second step, the limit as x approaches 2 of f of x. Okay, let's check this out. The limit from the right is 1. The limit from the left is 1. Therefore, the overall limit is 1. So check, the limit exists. So the first 2 work. The function is defined and the limit exists. Now the third step is the limiting value and the functional value must be the same. So the limiting value and the functional value must be the same. Well, remember what we got for our limiting value. We got 1. So these are not equal because 1 does not equal 3. So the limiting value and the functional value are not the same. Therefore, the graph is discontinuous at x equal 2. Okay, so that's what we want to kind of keep in mind here. These are how we're going to show these problems. You're going to show that you're checking for point continuity. You're going to show the steps, show which of the steps are satisfied, and draw a conclusion. Now there's different types of discontinuities. The first type that we want to look at is called a removable discontinuity. So we'll look at these graphically and then we'll see some other problems at the end of the lecture that kind of go over algebraically how we can work with these. But a removable discontinuity would be something like my nice little parabola I always like to curve sketch. So I have a removable discontinuity at C. Clearly I have a discontinuity here. Now the way I can make this removable is if I take this function and I define it at C in such a way that I have a continuous function. Now it wouldn't work to define it up here because I will not have a continuous function. Another example would be if I had my favorite parabola and I defined it at a value here. I can see I've defined it, but I haven't defined it well. So this one I have a problem with. I have a discontinuity that's removable here, but I have a problem because if I define this point right here to create this continuous graph, this point still causes me a problem. So you have to be careful which of these discontinuity type graphs that we're looking at. Now a jump discontinuity is as it says. To get from one part of the graph to the next, there has to be some sort of a jump. So a jump discontinuity might look something like this. Filled point, hollow point. And then I can see to move from here to here, there needs to be a big jump. So I have a jump discontinuity. Now the next kind of discontinuity that I have is called an infinite discontinuity. And we actually looked at this with a tangent graph. So with the tangent graph we had a lot of discontinuities. Let's go ahead and look at the graph of y equal 1 over x. Again, this is a graph that you should know exists in the first and third quadrants. It approaches both the x and the y-axis but never crosses them. Now typically when we write this we don't put in our asymptotic lines because they're kind of implied by how close these graphs get to both the x and the y-axis. But we can see here I have a discontinuity right here at the origin, but it's called an infinite discontinuity because on either side of this I approach positive or negative infinity. So that's an example of an infinite discontinuity, and we want to be able to talk about those different types of discontinuities and explain them. Let's go ahead and go back to a very familiar graph and a function by now that we're pretty used to looking at, and that's y equals sine of x over x. We looked at this graph a lot. Now what I would like to do is I would like to determine any discontinuities and see if they can be removed. Well, obviously where the denominator equals 0 I have a problem. So I'm pretty sure at 0 I have a problem. X equals 0, I have a discontinuity. So I have a discontinuity at x equals 0. Now the problem is I'm not sure if it's removable or not. Let's go ahead and look at a quick curve sketch, and again we've looked at this graph a lot. We have this hollow point up here, comes down and crosses and heads back up, crosses and head back up. Well, what I could do with this particular graph, this would be continuous if this was a filled point. So what I can do is fill that point. And the way that I can just do that is I can define this as a piecewise function. So I can take this and redefine it. I can say, well, my graph has sine x over x for every single value of x except x cannot equal 0. Now what I do next is I say, well, you know what? When x does equal 0, if I plug a 1 into my graph, I'll have this filled point, and now we'll have a continuous function. So I can create a function that is continuous now by adding that component to it. Let's go ahead and look at some other functions to determine if they have any discontinuities and whether they're removable or not. So let's look at y equal x plus 1 all over x squared minus 2x plus 3. Well, discontinuities occur where the denominator is undefined, or where a function has some sort of a value like a square root that I need to be careful with and not work with. But usually it's just working with the denominator. So in order to figure out what's going on here, let's try and factor the denominator. Now not every trinomial factors, so let's try x minus 3, x plus 1. And we can see that this works. So I have discontinuities at x equal negative 1 and x equal 3. So at x equal negative 1 and x equal 3, I have discontinuities. And then I notice, x plus 1 will cancel. So that basically means I was able to remove that discontinuity, but I'm still left with this problem in the denominator. So this is called a non-removable discontinuity. And all these characteristics of graphs that we're working with will kind of help us a lot when we get to a later section called curve sketching. Let's look at another graph. Actually, let's go ahead and look at the intermediate value theorem, and we'll kind of pull up a graph during that conversation. Now the intermediate value theorem, I want you to be aware of it. I don't think we're going to work a lot of problems with it. We'll work some, but not a lot. And we abbreviate IVT for intermediate value theorem. And this is the intermediate value theorem for continuous functions. And this is kind of interesting because the intermediate value theorem we live every day, and we probably don't even realize it for the most part. So the example I would like to use is your commute to school. So let's assume that you drive to school, and let's assume that you drive, let's say, on the interstate. When you start at your house, let's say at x equals 0, you're going 0 miles per hour. And then at some point you speed up, okay, and then you start to slow down. And I would like to know exactly what's happening at a particular point, let's say starting at A, ending at B. So the car is not stopping at B, it just is at that value of B, I'm getting an idea of what my speed is at that point. So start at 0, you drive, and this is what my graph ends up looking like. So at this very point B, I have some value over here called f of b, and that might be my speed, like 75 miles per hour, something like that. Now over here I have f of a, which in this case was 0. So what the intermediate value theorem says is this. It means in order for me to go from a to b, and if my function is continuous, I have to pass through every single value between whatever the y value is from my beginning point to whatever the y value is from my ending point. So back to the context of the problem that we were talking about, driving to work. If I go to work and I start at 0 miles per hour, and at some point along the way I take my quick snapshot of my speed, and let's say it's 75 miles per hour, that means that I had to go through every single possible speed between 0 and 75 miles per hour. I had to. I couldn't have jumped over anything. I couldn't have jumped over the gap between 15 and 20 miles per hour to get to 25. I had to continue through them all. So again, we live the intermediate value theorem every day. Well, what good is it besides the fact that it's very, very interesting? Well, it has a lot of applications in finding zeros and roots of functions. So it has applications in finding zeros, and roots of functions. So the way that this would work is, let's say we were looking at a graph and it was defined over some domain, and at some point A and some point B was the interval I was interested in. What happens between A and B is it travels and it's continuous. So because I know it's continuous, it doesn't have any gaps. Now down in this region, I know my value here was negative, and over here I know that it's positive. Well, by the intermediate value theorem, I'm guaranteed that because this travels from negative to positive values, it had to have traveled through 0, and that's called the 0 or the root or the solution of this particular equation or graph. Now we have to kind of be careful here though. It has a few little shortcomings. So the same example from A to B, I could start at this end and end up here. But what the intermediate value theorem says, well, if this happens, what it doesn't do is it doesn't guarantee the number of zeros. So, same thing, starts negative, ends positive, but in this particular case, I have a lot of zeros. I have one here and here, here. I have too many of them. So the intermediate value theorem doesn't say how many zeros I have, it just guarantees the existence of at least one zero. Well, there's one other thing that we need to look out for when we talk about the intermediate value theorem. For instance, in this particular graph between the intervals A and B, let's say my graph goes from this point to this point, that nice little parabola I always like. And what ends up happening is between A and B, I went to some negative value to some other negative value. And so you say, oh, there wasn't a change in signs, so it's not guaranteed that I went from a negative to a positive or a positive to a negative. The fact is I don't know if I only have the information that I went from a negative to a negative. In this case, the intermediate value theorem doesn't help us out because I don't have that change in sign. But no change in sign, and I still have two roots. So a graph goes nicely to work with the intermediate value theorem, and the deal is this. You have to choose small enough intervals. So between the interval in A and B, I wouldn't find my root because the interval is too big. But if I went to the interval, let's say between A and D, notice between A and D I switch from negative to positive, I would find that root. So again, you have to have small enough intervals for the intermediate value theorem to work. Okay, let's go ahead and look at a really interesting problem that kind of involves this idea of point continuity and then also looking at something algebraically. So here's the question. For what value of b is the function g of x, and this is kind of a step function or a piecewise function would be a better name for it, but I want to take the piecewise bit out of it, x less than -2 and then x greater than or equal to -2. So for what value of b is this function continuous at every x? So that's a question. So I need to find. Now when we look at this function, we can see that individually the graph of g of x equals x right here is continuous in and of itself. It's a nice line with a slope of 1 and a y-intercept at 0. Now this isn't defined over the entire domain. bx squared is actually a parabola, and what we don't know is if bx squared is a parabola that opens up or down, because those are a couple different options there. Now both of these are continuous in and of themselves, but what we need to consider is their domain. Now when we talk about the domains of these functions, we have to be pretty careful, because I see something very interesting occurring at x equal -2. So let's go ahead and talk about that a little bit more. So to start off with, let's go ahead and graph this piecewise function. Now when we graph a piecewise function, we have to be very, very careful about the domains of these functions. The graph of x, again, is just that nice straight line that bisects the first and third quadrant, but we're only considering this on the domain x less than -2. So if we plug a -2 in, we get a -2 out, but wait a minute, we don't have an equal sign there. So we had probably better put a hollow point in there for x at less than -2. Now I'm choosing values less than -2, so we'd go -3, -4, etc. So if I were to extend this line, it would bisect the quadrant. Next we're going to look at b equal x squared, which is a parabola that could open up, or it could be a parabola that opens down as well. Sorry, that's the up, the other one was down. We don't know which one it is, so we're going to have to figure this out by choosing that value of b, or figuring out what that value of b is. Now if b is positive, it will open up. If b is negative, it will open down. So what we do is we take bx squared and I set it equal to -2 at x equal -2. And the reason why we do this is, if I take that hollow point and fill it, what will end up happening then is I'll come up with a solution that fills this. So when we plug in and solve, I get 4b equals -2, divide through by 4, I get b equals -1/2. And right away I see the coefficient for my parabola, since it's -1/2, is a parabola that's opening down. So I'm trying to graph the function y equal -1/2 x squared for x values that are greater than or equal to -2. So if we plot these points, 0 is greater than or equal to -2, so if I plug a 0 in, I get a 0 out. If I plug a 1 in, I will get 1 squared times -1/2 is -1/2, and I realize that I have a parabola again opening down here. And again, I also knew it was a parabola opening down because of the -1/2. And I now can fill in that point at -2 to get a -2 back out for my filled point. So parabola opening down, and then as soon as I see this, I see my piecewise function. I have this linear function, and I also have this parabolic function opening down, and I can see that the entire graph is continuous now. Okay, let's go ahead and look at some other problems. This next one, I want to look at the function y equals 1 over the quantity x plus 2 quantity squared plus 4. Plus 4 is not part of the denominator. It's part of the numerator. Now what I want to figure out here is, are there any discontinuities? And if there are any discontinuities, are they removable? So to start with here, let's consider that denominator, because discontinuities occur where the denominator is equal to 0. So I can see pretty clearly here that at x equal -2, that denominator is equal to 0. So the next question is it removable or not? And the answer is, if you plot this in Maple, or if you plug in a -2, I can see that I'd have 1 over 0, which is undefined. 1 over 0 being undefined is kind of telling me that I have an infinite discontinuity here. So it's a non-removable infinite discontinuity. Let's go ahead and look at another function. X plus 3 over x squared minus 3x, let's go minus 10. Now discontinuities occur where the denominator is equal to 0, so let's factor and kind of set that equal to 0, and this does factor nicely into x minus 5, x plus 2, and the denominator will equal 0 when I have values of x equal -2 and x equal 5. So both of these are discontinuities. And because neither one of them cancel with the binomial in the numerator, I'd have to say that they're non-removable. And of course up top with this one was non-removable as well, but for a different reason. This was an infinite discontinuity. The second one we have also has discontinuities, probably with vertical asymptotes. Okay, our next problem, let's involve some absolute values. Remember, discontinuities occur where the denominator is equal to 0, which makes it undefined. And I can see when I look at this first term of the binomial that I need to have an absolute value of x plus 1 equals 0. So I need a -1 plus 1 equals 0. And there's no way -1 plus 1 can equal 0 if I can't get a -1. And as it turns out, no matter what I plug in for x, I get a positive value back. So there's no such value that I can plug into here to get 0 back out when I add 1 to it. Now the second term of the binomial is just a polynomial expression, x squared. The coefficient out front is a fraction, but it's still a nice polynomial expression that's continuous everywhere. So here, basically, this graph, this function is continuous for all values of x. There are no discontinuities here. Okay, let's go ahead and look at our next one. I love working with trig functions, so let's introduce another trig function. Y equal x plus 2 divided through by sine x. And again, discontinuities occur when the denominator of our fraction is equal to 0, or where it's undefined. Well, so we're trying to figure out where the sine of x is going to be equal to 0. Well, the sine of x is equal to 0, and it's so important that you know your unit circle. The sine of x is equal to 0 when x is equal to, and of course, because the sine function is periodic, it goes from negative to positive infinity. It's continuous on that whole interval. So I'm going to start out with x equal ... here, continuing the pattern, -3 pi, -2 pi, -pi, whoops, just one negative sign there, 0, pi, 2 pi, and 3 pi, and this pattern continues toward positive infinity. So the last time we looked at the cosine to see where it was equal to 0, we had odd multiples of pi over 2, but here we have integer multiples of pi over 2. And of course we're talking about integers, so we're talking about positive and negative values. So basically, if we want to shorthand this, we can say we do have discontinuities, and we have discontinuities at values of x that are going to be an integer multiple of pi over 2. So how would we write that? Well, that basically occurs at x equal n pi, where n, of course, is any integer. So when we're trying to work with these types of problems, you need to be pretty on the ball with your trigonometry. You need to know your unit circle, your trig ratios, and be able to work with your algebra efficiently as well in order to apply the calculus concepts.